Okay, so I want to end the course with a very brief introduction to applications of what we've done to probability theory. I will have one last video on after this on Lebesgue integration and measure in arbitrary dimensions, and I'll discuss Fubini's theorem. And talk a little bit about some of the theoretical aspects of probability distribution functions, when they exist, and so on. But there's not going to be any homework. Particularly, there's not going to be any problems on the last take-home exam based on the very last video. There is going to be a problem or two based on this video. Okay, so let's begin. So a triplet omega script f and p, where p takes f to 0, 1, is a probability space if, first of all, f is a collection of subsets of omega, and f is a sigma algebra. So here p takes subsets of omega, spits out a number between 0 and 1. And we think of this as, kind of measurable sets that we can measure. Particularly, we can measure the probability of. Okay. 2, probability of omega is 1. Okay. And 3, if the AIs are measurable, then the P of the disjoint countable union of the AIs is the sum of P of the AIs. Now, in general, if we just have P take f to 0 to infinity, including possibly infinity, and 2 is not necessarily true, then we say this triplet here is it's a probability space. Okay? Now, in that case, we usually don't use P. We usually use mu for well, actually, I don't think I'm going to write it, but usually instead of p, we have mu, takes f to 0 to infinity, script f to 0 to infinity. P is usually reserved for a probability measure. Okay? And mu, in general, is called a measure. Okay. So some kind of practical interpretations. A in script f is called an event. F, the sigma algebra F, is a collection of events that we can measure. And that's extremely important in applications of probability. In particular, often we don't want to just say F is the collection of all subsets of omega. That is a sigma algebra. We can do that. But in real life, we often don't have enough information to say anything about the probability of everything. Okay, like a practical example would be with the coronavirus. We just don't have enough information to say something about certain probabilities related to the coronavirus, for example. As more information comes in, we might be able to add to this collection of script f, events that we can measure the probability of. Often when you have a random variable, you might want to approximate that random variable based on certain amounts of information. So you might want to approximate that random variable based on having different sigma algebras of events. Right? That's a fairly advanced topic in probability theory called conditional expectations, which we will not get into. But that's something you probably would do in Professor Hildebrand's doctoral or graduate level probability course. Okay, and obviously P of A is a probability of A occurring, and P of omega equals 1 just means there's a 100% chance of something occurring. So for example, you could play a hand of poker, and omega could be all the possible hands in that one, all the possible outcomes in that one hand of poker. With 100% probability, one of those hands is going to occur. That's all it means that P of omega is 1. And it doesn't make sense to have more than 100% chance. That just doesn't make sense. I know you might have had a high school teacher or grade school teacher say you give 100% effort into something. That really doesn't make sense. Okay. So the simplest example would probably be omega is 0 to 1. F is just measurable subsets of omega, and by that I mean Lebesgue measurable subsets of 0 to 1. Let me move this down a bit. Okay. And here, P is just Lebesgue measure. And this is often called the uniform probability. It's just uniform probability on 0 to 1. Okay. Another example, extremely important, not terribly deep, but practically incredibly important, is just the overall general setting of discrete probability. And this absolutely captures that. Let's say omega is n. Let's say f is just the power set of n, all subsets of the natural numbers. For a is a subset of the natural numbers, p of a is going to be the sum of the pi's associated to a, where here these pi's are non-negative. So we're going to assume the pi's are non-negative. Right. And they sum up to 1. Okay. So pi is the probability that the integer I occurs, essentially. Okay. And you could also, you should be mindful that this setting handles the case essentially when we only want to look at, omega is finite. Why? You could just basically set all the pi's to be 0 except a finite number of them. And that practically takes care of omega being finite, even though really, you can put this into the general setting of omega, the whole natural numbers. But yeah, because there again, you're basically saying only a finite number of events can occur. Everything else has 0 probability. So okay, so practically it's pretty silly to talk about probability without random variables. So all a random variable is the outcome of an experiment. Okay? So a nice, easy, but still non-trivial example would be, let's say we flip an unfair coin. So we either have heads or tails. Little p, which is going to be something between 0 and 1. It could be, let's say as a matter of practicality, something strictly between 0 and 1. Okay. So that's the probability of flipping heads. And let's say little pi is going to be this here, where I is an integer. Let's say x is a number of coin flips. If we flip until we get 1 single heads. And these flips are going to be assumed to be independent, so one flip doesn't affect the other flip, or any subsequent flips. Okay, so I claim that the probability that x equals I is pi. Let's just check that for a few I. Let's say I equals 1. That means we flipped the coin. We got heads because we stopped at 1 flip. Okay, well, we know that's going to be p. That's the probability. So that matches. When I equals 1 here, this goes away. Let's say x equals 2. Okay, that means we flipped twice. Okay, so we had to have flipped tails, heads. Because if we flipped heads first, then we would have stopped. So we would have only flipped it once. Okay. And if we got tails, tails, then, well, we didn't stop. We're going to keep going until we get heads, so we did not stop at 2. So if we stop at 2 flips, we have to have tails, heads. And plug in I equals 2 here. It's 1 minus p, and that's exactly the probability of tails, which is 1 minus little p, times probability, that's exactly probability of tails and heads, because it's 1 minus p, the probability of tails, times p, the probability of heads. Okay, one more, I equals 3, x equals 3, same logic, it's tails, tails, heads. So it's 1 minus p squared p. So, right. Okay. And we called pi the PDF of x because it gives you the probability that big X is I. Okay. And in this case, we say x is discrete because, there's only a countable or finite number of possibilities for x. I mean, really, like I said, you always, in general, can consider x can take an infinite number of possibilities. Just you can say, except for finitely many of them, they're all going to have 0 probability of happening. So in that sense, x, the number of possibilities being x, for probability's sake, really still follows under this general framework. Okay, so probably more practical is, in terms of like actual real-life applications, is continuous random variables. So in this model, for a Lebesgue measurable, the probability of x, probability that x is in A, and here we're only considering univariate random variables, meaning just real-valued random variables. I'll briefly talk about multivariate random variables that take on values in RD. But yeah, I mean, in practice, it's extremely valuable to consider multivariate random variables. I mean, but we only talked about Lebesgue integration in one variable, so that's why I'm going to have one last video where I'll talk about all these things in the d-dimensional case. But anyway, so for a Lebesgue measurable function and x a real valued random variable, we're going to assume the probability that x is in A is given by this integral here for some measurable non-negative function f, where the integral over all of R is 1. And that's just the probability that x is in R, which has a 100% chance of occurring if x is a real valued random variable. And we say this is PDF of x. So one fascinating question that we would have completely answered if we had more time in this course is, given a random variable, when does a PDF exist? So in undergraduate probability 362, you just take the existence of a random variable for granted, which you kind of have to do. You can't answer that question without taking this course. That you just need this course to answer the question, and this question is actually completely answered in section 6.4. So it's actually it's 2 chapters after the chapter on Lebesgue integration. So and it has to do with absolute continuity, but anyway. So 2 examples. One most ubiquitous, of course, is the normal distribution because of the central limit theorem. So for example, if you wanted to take 2,000 random SAT exams and looked at the scores, that would be modeled by a normal distribution. Sigma is the standard deviation, M is the mean. Or exponential distribution, which would model, a lot of times give a simplistic model for the, how long a machine part or a, electronic component lasts. Well, where X is how long it lasts. And here X is bigger or equal to 0. And lambda is just some parameter. Of course, there's a lot, many others, but two simple examples. And lambda here is positive. Okay? So you can check that this integrates to 1 absolutely trivially. This one is a little harder. You may have done it in Calc 3, but anyway. Okay, so one of the highlights of this course, which really took an enormous amount of work to do, but it was worth it. So one of the highlights of this course is that given probability as described above, in terms of a continuous random variable, so we describe P in terms of this probability distribution function. So we proved that if script F, our collection, our sigma algebra of measurable sets is the collection of Lebesgue measurable sets, then this is a probability space. In particular, P, as described here, is countably additive. Okay. And this is extremely important. This says every theorem you prove about probability spaces applies to the case of a continuous random variable. Okay. So what I want to do next, to give a non-trivial example of some results in probability, I want to prove the Borel-Cantelli lemmas. There's two of them, actually, for probability. One really doesn't need probability theory. The other one, is one we've essentially already proved already, and you can prove without any notions of probability. The second one really is a probabilistic result. And from that, I want to prove something highly non-trivial in probability theory, which is called the 0-1 law. There's a lot of them out there, and but anyway. So first, we need the concept of independence. And you've all seen this before. Let's say A and B are measurable, so they're in the script F, where F is sigma algebra of subsets of omega, and we have this associated P to those two. These are independent if the probability that A intersect B is probability of A times probability of B. So if it's been a while, here is an example of two independent sets. So let's say let's say I go get a haircut, and I do want a haircut. I really want a haircut badly, but not sure where to get one, and I'm not sure if I trust my girlfriend's mother to give me a haircut. But anyway, so let's say I do get a haircut, and usually it's good. I usually actually get it at Megan's and Slingerland's, but let's say it turns out to be good. I would say more than 8 out of 10 chance it's good, but let's just say 8 out of 10 chance, 80% chance my haircut is good. Okay. Let's say I buy also a pack of M&Ms. Let's say I pick one out at random. Let's say the probability that I pick a yellow M&M out is 10%. I don't know if that's true. I haven't bought M&Ms in a while, but so getting a good haircut is completely irrelevant to pulling a yellow M&M, assuming I did purchase this bag of M&Ms. Okay, so from that regard, the probability that both of them occur is going to be 8%. It's just intuitive that we just multiply the two probabilities together. I mean, I have 8 out of 10 chance the haircut is good. 1 out of 10 chance I get the M&M. The M&M I pick randomly is yellow. So 8 out of 100 chance that both of them occur. Okay. Now you can't say anything about, let's say, probability. You can't really say anything about I get a good haircut and I purchase a bag of M&Ms necessarily, because they might not. Those two events are not necessarily independent. If I get a crappy haircut, I might be grumpy and say, well, I want to treat myself to a bag of M&Ms. I feel like crap because of this bad haircut. On the other hand, if I get a good haircut, I would probably think, well, I'm not going to buy this junk. I'm happy with my good haircut. So, okay, so right. So I'll talk more about independence in a moment. So some basic facts about probability spaces. Proofs are very easy. We've gone through basically all of them, essentially. Not exactly, but essentially. Probability that B takeaway A is probability of P of B minus P of A. So saying probability. So, and this is if A is a subset of B, and that's very easy to prove using countable additivity. And I should mention, just like with Lebesgue measure, built into this is finite additivity by setting all but a finite number of the AIs to be the empty set, and you can prove very easily that the empty set has 0 probability. So, yeah. Okay. With that in mind, right. So, so a consequence of A is that P is monotone. So, interestingly, for Lebesgue measure, we needed countable subadditivity to essentially prove countable additivity. Countable additivity actually fairly easily implies countable subadditivity in general. It's a very easy consequence of going back to the disjointification process that we discussed way back. And proving this, I'll leave as homework that I'll collect in the last homework set. Okay. And we have the all-important continuity of measure. If we have a sequence of measurable sets, and we take the union, which is still measurable because script F is sigma algebra, and if these are ascending, then P of A is the limit of the P of the AIs. And we have the same thing with nested sequence of measurable sets. P of A, if A is the intersection of the AIs, is the limit of P of the AIs. So for Lebesgue measure, this was true. Well, D was true in general. E was true if the measure of A1 is finite. Well, for probability space, we don't have to worry about that because probability, the P of A1 is at most 1. That means it's finite. So I should mention 2 is not needed for A through D, and in general, E is true if P of A1 is finite. And so what I mean by that is, like I was saying before, we call this triplet a measure space if P, in general, we have this function here taking f to 0 to infinity, and this here is not necessarily true. This could be anything from 0 to infinity. Okay? So without this condition here that this is equal to 1, everything I said is true. E is true if the measure of omega is finite. Or sorry, the measure, well, certainly that's true. In general, E is true if the measure of A1 is finite. Okay? And again, really, usually P is reserved for a probability measure, and generally use the letter mu. Okay. Okay. And the proofs are identical to the proofs of, in general, proving, the proofs are identical to the proofs for Lebesgue measure, thanks to countable additivity. All right. Okay, so let's see how these are used, and an example of how these are used in probability. Okay. So we first need the non-trivial definition of independence for a sequence of events, and you might have done this in 362. So we say a sequence of events are independent if for any finite subset of the natural numbers, the probability of this intersection is a product of the probabilities. And this makes sense. This is, and this is basically saying, the AIs don't depend on each other. So it's a natural generalization of the independence of two sets. Okay? And you cannot just assume I is of the form 1 to k for some integer k. I don't want to go and get into this because I don't want this video to be too long, but if you go back to your 362 book or your 362 course, you probably showed by example that that's a crappy definition for independence. It just doesn't work. Right? You really need the flexibility, and we'll see that in what we're going to prove, that you need the flexibility that I can be any subset, any finite subset of the natural numbers. Okay, so to illustrate why we need that flexibility, let's prove the fairly intuitive fact, though it's a pain in the ass to prove. It's easy, but it's still a pain in the ass. So this came out a little crappy. Okay, so right, so give me 1 second. Go. Okay, sorry about that. So a sequence, the AIs are independent if and only if the complement of the AIs are also independent. That makes sense. If the probability that the AIs occur don't really depend on each other, then probability that the AIs don't occur should not depend on each other. Okay, and let's see how this is proved. It's a neat little proof, I think. So before I do that, I want to comment that we can actually extend. So if we have these AIs are independent, then we can actually prove this is true for any possibly infinite subset of the natural numbers. It's not terribly surprising necessarily. But one important point of this is that implicit in this is that this product, this infinite product exists. Okay? And by definition, this infinite product is just the limit of the finite product of I in little I and big I intersect, let's say, the set 1, 2, all the way to n, where n goes to infinity. Okay? So yeah, implicit in this is that this infinite product even exists, which is not trivial. though it is a consequence of countable additivity. And I should mention along those lines, implicit in, just like with Lebesgue measure, implicit in countable additivity is that this infinite sum exists. There's no ambiguity of whether this probability exists, because script F is a sigma algebra. If the AIs are measurable, then the countable union of the AIs, disjoint or not, is going to exist. Okay? But so implicit in this assumption is that this infinite sum exists. So this is a powerful assumption, right. So 2, we're going to leave as a homework that I will put on the last homework, the last take-home exam, because it's a really nice application of continuity of measure. Okay, it's a really, really nice, simple example of continuity of measure. Okay, and remember, again, implicit with continuity of measure is that these limits exist. Okay, so and you really should be able to pretty quickly imagine how you would use continuity of measure to prove 2. Okay, so let's prove 1. This is, like I said, it's not hard, but it's tricky, and it's not very intuitive. And it's just a neat proof, a neat proof of fiddling around with probability stuff. So what we're going to do is we're going to prove that the AI is independent implies that for any k, this modified AI primes, where it's the same thing as the AIs, except at the kth slot, we remove AK and replace it with AK complement. Okay. So I'm going to prove that if the AIs are independent, then the AI primes are also independent. If we can prove that, well, then let's say k equals 1. Then that's going to mean that A1 complement, A2, A3, this is an independent sequence of events. Well, let's repeat that. So we know this is independent, so let's say k equals 2. Then we know A1 complement, A2 complement, A3, et cetera, are independent. Let's apply it to this sequence. We know that then k equals 3, setting k equals 3 rather, A1 complement, A2 complement, A3 complement, et cetera, are independent. And then we can keep going and going and going to basically capture everything. More rigorously, you should check that just being able to keep going and going and going is enough to prove that the AI complement, these are independent. Okay? So let's prove this. Okay. So so what do we have to prove? We have to apply the definition to the AI primes. We have to prove that for any finite subset of the natural numbers, big I, that this is true. Well, we're applying it to the AI prime, so we need to prove this is true. Okay. Okay, so let's get to work. Right, so we need to prove this is true for the AI primes. Oh, sorry. Okay, so if k is not an I, well, then we know the AI primes are just AI, okay? So in that case, well, we know this is true. Why do we know this is true? Well, we know this is fairly trivially true. Sorry about that. We know this is true if k is not an I, because all of the AI primes in that case are just AI. AI prime is AI, except if I is k, in which case it's a k complement. Okay? Right? So, yeah, this is trivially true. Okay? Because of independence. Okay? So because this is true, thanks to the independence of the AIs, we know that if k is not an I, then this is true. So let's assume k is an I. So for convenience, let's say A is a k. Let's say B is the intersection of the AIs over all little I and big I except k. So let's make an observation that A and B are two independent events. Why? Well, A intersect B is obviously this intersection here. That goes without say. I mean, this is the intersection of the AIs without the k. Here is k. So this is just the entire intersection. We know the AIs are independent, so this intersection, the probability of the intersection is a product of the probabilities. Okay, we can trivially write this as probability, P of AK times a product over all little I and big I without the k. But, and here is where we need the flexibility of independence as is given in the definition we described. So I take away k is a finite subset of the natural numbers. So apply independence to that subset, that finite subset of natural numbers. So this product here going backwards is the probability of this intersection here. Well, I mean, trivially, this is A, this is B. That's how we defined A and B. So this is the probability of A times the probability of B. Okay? So these two sets are independent. Now let's put this to good use. Okay? So again, the AI primes are the AIs unless I is k. If I is k, then AK prime is AK complement. So just rewrite this intersection as AK prime intersect this intersection AI prime, where little I is and big I, take away k. So that using what I just said, this is just AK complement intersect this intersection here. And that's exactly AK is A, B is this intersection, so this is A complement intersect B. Okay, well, that's the same thing as B take away A. Okay. Well, that's the same thing as B take away A intersect B. That's just, you can prove trivially 299 stuff. B take away A is the same thing as B take away A intersect B. Okay, and now we can use that excision property because certainly A intersect B is a subset of B. So this is probability of B minus probability of A intersect B. But A and B are independent of each other. So that's probability of A times probability of B. We can factor out the probability of B. And because we are in a probability space, probability of B, sorry, 1 minus probability of A is probability of A complement. So really, it's probability of B times probability of A complement. I just switched the order. Okay. Now let's again go backwards and use independence. We already mentioned that the probability of B is a product of these probabilities, thanks to independence of the AIs. Okay, and A is A K, so A complement is A K complement. Okay. Well, finally, again, A K prime is, AK complement is AK prime. AI is AI prime if I is not K. So this whole product here is exactly this product here. And this is exactly what we want to prove. Probability of this intersection is product of these probabilities. This is a little faint. Not that it should really cause confusion, but so my cell phone doesn't do a great job of taking photocopies unless I really push hard on my pencil, which I don't sometimes do, but anyway. Okay, so in general, let's describe something, let's talk about something we've already seen, but outside of a probabilistic context. So let's say in general, not necessarily independent, but let's say we have a sequence of events. So the intersection from k equals 1 to infinity of this union n equals k to infinity of the ANs, which is measurable if each of these AIs is measurable, because again, script F is a sigma algebra, and we're assuming the AIs are measurable. Whenever we say something is an event, we assume it's in script F. Okay? So this is the event that AN occurs for infinitely many N, and I and other probability texts, like graduate level probability texts, call this AIO. IO is abbreviation for infinitely occurring. So AIO is the event that infinitely many of the ANs occur. So yeah, I for infinitely, O for occurring. Okay. So why is this a good model for the event that AN occurs for infinitely many N? Well, we actually proved this, and by that I mean I believe I gave this for homework many weeks ago, that X is in big AIO if and only if X is in AN for infinitely many N. Homework was literally X is in AN for infinitely many N is equivalent to X is in this set here. Okay? So yeah, the equivalency of these two was exactly what was homework. And really, we just need an abbreviation for this, because it's a pain in the ass to write this so many times. Okay, so what I want to prove, and the first one we've practically proved already, the first Borel-Cantelli. We proved it for Lebesgue measure. The general proof is identical, literally identical. So if the sum of the probability of these ANs is finite, then with zero probability, the event that infinitely many of the ANs occur has zero probability. Okay. On the other hand, if I have a sequence of independent events, and this sum is infinite, then the probability of the event that infinitely many of the ANs occur is 1. So this leads to this interesting probabilistic phenomenon that, again, if you take a serious graduate level probability course, you'll see in various manifestations of this. This immediately leads to a very simple version of the 0-1 law, which in this case says that if we have a sequence of independent events, then either the probability that infinitely many of the ANs occur is 0, or the probability that infinitely many of the events occur is 1. There's nothing in between. It's either 0 or 1. Well, why is that a consequence of 1 and 2? Well, let's say these are independent. Then either the sum is finite, in which case this has 0 probability, PAIO is 0, or the sum is finite, sorry, or the sum is infinite, and PAIO is 1. Either the sum is finite or the sum is infinite. There's no other choice for an infinite sum of non-negative numbers. Okay? And we know that from 511, that a sum of non-negative numbers is either converging or infinite. Converging meaning it's finite. Okay, so yeah, that's a really neat neat application of these two results. So let's prove 2. Okay, so like I said, 1 is homework. I'm running out of problems I can even assign for you to do for this last homework set. So I don't know if I'm gonna give this as I don't know if I'm gonna assign it. I might not, because literally it's identical. So you can basically just change notation. Well, anyway, I don't want to say more, but okay. So 2 is a nice little proof. So first, and one thing I love about this proof is you can never escape basic 511 stuff. It's just you can't escape it. You always have to be knowledgeable of 511 stuff. I mean, first of all, I mean, just the 511 fact that either an infinite sum of non-negative numbers is convergent, i.e. finite. Sorry, it's either convergent or infinite. That's just something that, you can't escape. You need to remember. Second, you need to always keep into the back, keep in the back of your head these little estimates that are proved by the mean value theorem. And particularly, we'll need that 1 minus x is less than or equal to e to the minus x for x bigger or equal to 0. Why is that true? How do you prove it? Graphically, it's obvious, because 1 minus x is the tangent line for e to the minus x at x equals 0. So, I mean, you got the tangent line, here's the tangent line, and you basically, let's say 0 is here. You have 1 minus x being like, more like this. So yeah, it goes like that. Okay. So intuitively, e to the minus x sits above the tangent line. You can rigorously prove this very easily using the mean value theorem, like you've done in 511 a million times. So when x equals 0, both sides are equal. Let's differentiate both sides. Left-hand side has derivative minus 1. Right-hand side is minus e to the minus x. For x bigger or equal to 0, minus 1 is always less than or equal to minus e to the minus x, because e to the minus x is less than or equal to 1 for x bigger or equal to 0. So by the mean value theorem, that proves the claim. Okay. So first of all, I want to set this up in a way that I can use continuity of measure. So how do I do that? Well, you do kind of the obvious thing. Maybe not quite the obvious thing, but you do basically the obvious thing. So let's say EK is the union from n equals k to infinity of AN. Okay. So this is clearly nested. K equals 1 is the union of all the ANs. And as k gets larger and larger and larger, we're just taking the union of fewer and fewer and fewer of the ANs. So this is definitely nested. So, and also by definition, PAIO is the intersection of the EKs, because AIO rather, is the intersection of all these. And, well, let me get rid of this here real quick. So the erase feature is not as nice as I would have liked on Adobe Reader, but I guess I can't complain since Reader is free. Right, so yeah, by definition here, this is EK. So we're defining this as EK. So the intersection of the EKs is AIO. Okay. So we have a nested sequence of measurable sets, a nested sequence of events. We can invoke the continuity of measure. Again, by definition, AIO is this intersection. So by continuity of measure, this is this limit. Okay. So now I'm going to use the fact that probability of EK is 1 minus the probability of EK complement. Okay. Now by De Morgan's law, because EK is this union, EK complement is the intersection of the complements. Okay. And we're going to show that this here is 0 for any K. And so I want to do this. I need to do this because independence says nothing about unions. Independence only says something about complements. Okay. Now, I'm assuming the AIs are independent. We proved that means the AI complements are independent. And homework is that P of the intersection of any subset I of the natural numbers of an independent set is the product of these probabilities. Let's apply that to I equals K plus 1, K plus 2, et cetera, that infinite subset of natural numbers. So because we know the AN or the AI complements are independent, that homework tells us that the probability of this intersection is the intersection of the probabilities. And in particular, this infinite intersection converges. Okay. Let's go one more time, go backwards, and use the probability of AN complement is 1 minus probability of AN. Now let's use that fact that we said is true from the mean value theorem. This is less than or equal to e to the minus probability of AN. Certainly probability of AN is bigger or equal to 0. It's less than or equal to 1. We don't care about that. But so continuity, just regular continuity, says that this is going to be equal to e to the minus the sum. Because e to a sum, well, we know e to a finite sum is the product of e of the sum's factors. And by continuity, that extends to infinite sums. Okay. Right. So this is going to be 0. We know this is going to be 0 because, well, this sum is infinite. And this sum is infinite precisely when this sum here is infinite. And this might be a little hard to read. But here, this is the sum, same sum, but over n equals k. So in general, this is not necessarily true, because in general, we don't know much about, well, the measure of AN. But we're dealing with probabilities here. So, well, so I don't want to do that here. So each one of these is between 0 and 1. So in particular, each one of these is finite. Okay. So this is infinite if and only if this is infinite, because, well, we can just take the contrapositive. This is finite is equivalent to this is finite because, well, I mean, any finite number of the probability of the ANs is finite. It's between 0 and 1, so any finite sum of the probabilities of the ANs is also finite. So the tail is infinite. Tail is finite if and only if the whole sum is finite. Okay, yeah, that basically proves it. Yeah, and if this is hard to read here, I should fix this a little bit. This is just AN. So, okay. So what I would have liked to have done is discussed independent random variables, um, which intuitively is not hard to describe, but to carefully do it would take way longer than I would have liked. But I might just scratch the surface in one more video, but yeah. But this is all you need, this video, for the take-home exam. So hopefully you found this interesting, and maybe it inspired you to continue on in probability theory. And a good point of continuity from this video is actually, I'll put a link up in Blackboard, is Lawrence Evans' book on stochastic differential equations. It talks very briefly about a measure theoretic perspective of probability, repeating a lot of what I said in this video, and then describes kind of calculus and differential equations using probability theory, which is extremely practical, extremely important to just about any practical science and engineering field imaginable, because in real life, things do change in time, and there's probabilities, there's uncertainty associated to these events that change in time. And you would still like to describe, rates of changes for these random, events occurring that depend on time. That's exactly what stochastic differential equations do. Stochastic meaning random. Okay. And really, this course, largely in conjunction with this video, will have prepared you for such a study of, well, maybe in conjunction with this video and the next video, will largely prepare you to read such a book. All right, well, this was a long video, so I'm going to shut up now. And so long, take care. This is the last day for lectures, so you've made it. You've just got the exam left, or your other exams. So, all right, so long, take care, stay safe, and don't forget to do the evaluations. You have, I think, 2 days left to do those. So, bye-bye.